Hello everyone, I hope you're doing well. So before starting today's video, I just wanted to discuss something about yesterday's question. So this is yesterday's question and I can also reload this page for you. So this is yesterday's problem, which was the problem of the day, and something very weird happened. So first things first, I want you to have faith in this particular thing that whenever I upload any solution or explanation, it is only uploaded after due diligence and checks from my side. Right. I do not upload any solution just right away. I check it, I submit it myself. Only then I upload any solution. Right. So be it either Code Forces solutions or like Geeks for Geeks explanations, it is already done after I've submitted the code myself. But there might be instances like in Geeks for Geeks when the problem statement later changes because all the things I do are like early in the morning around 6 or 7. So there might be a case when the problem statement might change later on or the test cases itself change later on. Like they might find that some test cases are not enough. They might add others or remove some of them. Right. Same thing might happen with Code Forces as well. Like it can be like during the contest I submitted some solution and it passed the pre-tests, but later on after the system testing some of the pre-tests some of my solutions failed. Right. So it is very well possible, but when I'm uploading the video I just make sure that my solution is working. And if you ever find that the given solution or the given explanation is not correct or it is failing in some test cases, what you can do from your side is you can just mention it in the comments and I'll definitely look into it and provide I'll update the pinned comment or I'll just do whatever I can do from my side. Right. So in case you are wondering, I can also show you. So this was yesterday's problem. If I go to my submissions, you can see there are two attempts where my time limit exceeded. So this is something I was trying. I was trying some other approaches as well. Now one of my solutions got accepted at 624. Right. And now if I show you this particular solution, this is the exact same code that I explained in the video. Right. This is the same thing. But when I got some comments that it is not working, I submitted the exact same solution at 10:45 again. You see that this is showing wrong now. And if I open it, this is the same wrong solution. Right. So when I realized that these are the test cases it is failing, what I did was I went through those test cases and submitted my final solution again at 10:46. So this is the final thing that I updated in my GitHub also. So all the codes are generally updated and maintained in my GitHub repository for Geeks for Geeks. So in any case, like you want to check it out, you can also check it out. But rest assured, if there is any time like you feel that the code is not working, then you can just politely ask it down in the comments. And I saw some comments. I don't know whether the user removed it later on. Like he was trying to spam the comments by messaging the same thing that it is not working, not working. So I'll just request you all that have faith in this particular thing, that all the codes are only all the solutions that I explained here are only explained to you after they have been verified. Like there's no such thing that I'll be just posting videos without checking. Right. So I want this faith from your side. So that's it. I wanted to say. Now let us quickly start with the problem of the day. So today's problem is nearest smaller tower, and it is a medium level problem. So the problem says that we have been given an array where each element, array of height, represents the height of the tower, right? And for each tower, the nearest possible tower shorter than it. Like we have to find the nearest possible tower that is shorter than it. So we can look on both left and right side, and they have also given some extra conditions, right? So whenever you find these types of questions, a very correct approach to approach these side of problems is using a stack. Right. There are also other approaches to solve this particular problem. I'll also be discussing them, but mostly this is a very standard problem, and the only difference is that they have added some extra nodes here, and they have added some extra conditions. Generally, what this problem is you have to find the smallest tower to the right of it or to the left of it. But now we have to look on both the sides, and will have to take care of these conditions. So the code will become a bit lengthy, right? Otherwise, it will be the exact similar implementation. So we are going to need this particular thing later on. So let me just copy it and we'll discuss a sample test case. This is very important because it has the important conditions that we need to take care of. Right. So I'll have it with me. So let us discuss a simple test case that has been given to us in the input. So it is 4, 8, 3, 5, 3. Right. Now we have to find the smallest nearest tower. Right. So for example, for this particular index, that is 0th index, let me just also write the indexes. Right. So for this particular index, we have 4 here and we want to find a number smaller than it. So you see that 3 is the nearest smaller number to it on the right of it. So the answer for this particular index will be 2. Right. Similarly, for 8, 3 is the nearest smallest number. So the answer for this particular index will be, let's say 2. So 3 is the smallest number itself. There will never be a smaller number than 3. So you will see the answer is -1 for this. And again, for this particular index, you see on the left is 3, on the right is 3, right? And both are of the same heights. So you will see that it is case where of the second condition, if two towers have the same height, then we choose the one with a smaller index. So we will have to choose 2 instead of 4. Now again, for the last index, it is -1. So this is a second sample test case that has been given to us in the input. Now let us discuss some approaches of how we can do this. Let us first discuss the brute force approach. So the brute force approach is, this is a brute force approach. Now what you can do is, for any index I, right, you can take a variable x, right? What is x? Now x will start from 1 and can go up to n, right? So what you will do is, you will go to I minus 1 and I minus x and I plus x at the same time, right? So for example, if you were starting from this particular position, you will jump to here and then here at the same time. You will check their values and compare them with the original value as well as among themselves, right? So why among themselves? Like you will have to take care of these two conditions, right? So the main condition is that the tower should be smaller than it. You have to find the tower such that it is nearest to it. Now what happens when there are two towers at the exact same distance? Right, this is the main point, and these are two towers at the exact same distance. Now, and both are smaller than the current element. Now, we will have to compare these towers among themselves. So the first condition is that we have to pick the smallest tower. We have to pick the smallest tower. If two towers are at the same distance, they both are smaller than the main tower. So we have to pick the smallest tower among. Now, what if the height of both the towers are equivalent? Now we have to pick the one with the smaller index first, right? So this way we'll have to take care of multiple conditions, right? So whenever you do I minus x and I plus x, you can go in both sides and check, first of all check with the main tower, and then if both are satisfying that condition of the main tower, then definitely you would have to check them among themselves. So first of all, it will go to 1 to the left, 1 to the right, then 2 to the left, 2 to the right. This, it will keep on going and exploring, right? Now the value of x can be at max n, and obviously if like for example, if this was at the second position and there is only one cell to its left, then on the second on the second iteration it will go out of bounds and you'll have to take care of it separately, right? And this right one will still keep on going on the right? So that is why I have taken it to be n, but if one of them goes out of bound, you will have to take care of it separately. Now the overall time complexity is, you will have to traverse I from 1 to n and x from 1 to n also. So the overall time complexity is of n square, right? This is definitely not going to work in our case, because n is up to 10 to the power 5 here. Now let us discuss a much better approach which is going to work in O of n, right? So this approach uses stack, and it is a very common approach, like you will find it everywhere, and like more popular, it is used in more popular problems as well. So the key idea is, like you start traversing from the left. Now let us assume for a second that we don't have to traverse from the right. We are just concerned about the smallest element, or the smaller element than the current element that is present to the left of it, right? So for example, if we have an array like this, right? So this is our array, and we are currently at this index. We are concerned about the nearest element that is smaller than this particular element, right? So let us not think about the right part now. We are only concerned about the left part for each index. So what we'll do is, we'll maintain a stack, right? Whenever we get at an element, right? So we'll have some elements at the stack. So for example, it is 10. Now we will have some elements in our stack. Let's say we have 7, 8, let's say 20 and 30. Right. Now we will keep on popping elements. We will keep on popping elements from here until the top element of the stack becomes less than the current element. Right. Why? Because we want an element lesser than the current element, and the element lesser than the current element is 8 here. Right. So now what happens is we will have to pop this particular 30 and this particular 20 from the stack. Now the stack remaining would look something like this, 8 and 7. So since this particular 8 is smaller than 10, then we'll also have to maintain an index for it. Right. For example, in index I was associated with it. So let's say like 8 was present here and its index is 3. Right. So we see that the top element is 8 now. We will catch its index, that is 3, and store and store this particular value in our answer. Right. So the key idea is we keep popping elements from the top of the stack until we find an element that is just smaller than the current element. So why this approach always works? So for example, we had an element 15 here after 10. So what will happen is if 8 is smaller than 10, this is the case when the next element is greater than the current element, right? If 8 is smaller than 10, then it will also be smaller than 15, right? So it will always work for 15 as well. But you will always see in such a condition that 10 will itself work for 15. So you will never have to come to 8. Now what happens when the next element is smaller than the current element? So let's say it was 9, right? So 10 is not going to work for 9, but there is a chance that 8 might work for 9, right? So you see that if the next element is even smaller than 10, then 30 and 20 that were not working for 10 are definitely not going to work for 9 as well, right? So we discarded them. And that is not a waste operation, right? That was not some useful information that might have been helpful later on, because we have already found an element that is going to work for us, and that is 8 and 10 here, right? So if the next element is greater than 10, then 10 is going to work. If the next element is smaller than 10, then 8 might work and 8 might not work, right? But 30 and 20 were definitely not going to work, right? So this is the key idea behind this concept of pushing elements into the stack and popping elements into the stack, right? So whenever the top of the stack is greater than or equal to the current element, so we will keep popping it, and whenever we find an element such that it is smaller than the current element, then we will keep it. And after all that we have stored this information of index I for the current value, what we'll do is we'll just push the current element into the stack like this, right? So the final step after this operation at this particular index would look something like this, and then we will move on to the next index and repeat the same process. Now let's say we have done this particular thing, but we wanted to also find answers from the right side, right? Now we are going to repeat the same process. We're just going to do it from the right side. Now while doing it from the right side, we'll have to take care of certain things, right? So for example, the first thing that we have to take care of it is like we have to find the nearest possible tower. We have to find the nearest possible tower. So like this was the first condition. Now what we'll do is we'll have an intermediate array which will store our intermediate answer, and we will have our stack which will store all these values. Now since we have to find the index and we are also concerned about the distance, right? So like instead of just storing the value of the arrays, we are going to store a pair. So it will be a pair of values. The first so let me just write it first, in comment, right? So the first value can denote the actual value that is present in the array, and this can denote the index, right? So this information will be very useful when we want to calculate the distance, when we want to calculate like the nearest element and so on. So we will initially store all our answers in our intermediate array, right? So while traversing from the right, what we will do is we will just make sure whether the intermediate array like has been updated or not, right? There might be some elements for which a smaller element might not exist on the left. It only exists on the right. So in that case, the intermediate array will not have any value. So if it does not have any value, we can just directly assign the value to it while traversing from the right, right? So we can directly assign our value or whatever we have directly to it. Now in case it already has a value, we have to compare certain things, right? So let's say that the new value that we have got is a candidate value. right? So we will have an index associated with the candidate value. So let's say there was one more value which is old dot index. So old dot index will be the old answer that we have got while traversing from the left, right? So if you have the index of both of them, we can definitely compare their distance, right? So if x was the old distance and y is the new distance that we are getting, right? So if y is less than x, then definitely we have to update our answer because we have got a smaller distance. Now if x is equals to y, then we will have to compare the rest or the remaining two conditions. If x is less than y, then definitely the old distance is smaller than the current new distance. So we don't have to change anything. So like in this case, we have to do direct update. In this case, we'll again have to check the remaining two conditions, right? So the first condition is if two towers are at the same distance, pick the smallest tower. So let's say that D1 is the height of the old tower and D2 is the height of the new tower, right? So if D2 is smaller than D1, then direct update again. Otherwise, if D1 is equal to D2, if the distance of both of them is same, again we will have to evaluate two conditions, right? That is the final condition. Under this final condition, we will have to choose the one with the smaller index. So let's say I1 and I2 are two indexes. So I1 is the old index and I2 is the new index. So only if I2 is less than I1, we will have a direct update, right? And we have to ignore the other condition. We don't have to do anything in any other case, right? So this will be the whole flow, right? You just have to update the values. You just did a normal traversal from the left first, and while traversing from the right, you just have to check whether I have got a better answer or not. It's just the same as putting the direct answer, but before just putting the direct answer, we have to check whether I have got a better answer or not. Only if I have got a better answer, I'll update the value, right? And after all of this is done, after all the traversal is done, we had all the values in the intermediate array and we'll have to convert it into the final answer vector, right? So this is what we are going to do. So I'm just going to quickly summarize what I just said. So the key idea is of using a stack that we already have seen in many other problems. The only difference is in the similar problems that are like standard problems, what they do is they just try to give you traversal from one side. So we have to find the next smaller element to the left or next smaller element to the right. This is like a little bit upgraded version of that problem. We have to check it from both left and right on the basis of certain conditions. So what we just do is we do a traversal from the left, and while traversing through the right, we just do the same thing but instead of putting the values directly, we compare whether the new value that we have got is better than the previous value or not, and only if it is better, we are going to overwrite it over the previous value, right? So this is our whole idea. Now let us have a look at the code and discuss the code now. So what we're doing is I've created a variable n equals to array.size, and we have created a stack of pairs, right? Similarly, a vector of pairs called inter. So this is going to store my intermediary answer. So I've initialized all the values with -1 comma -1, and this will indicate that I have not got an answer for this particular index till now, right? Now I just traverse from the left, so you will see that this part is very simple. While this statement will check whether there exists some element in the stack, right? Now I just compare whether the top element is greater than or equals to the current element. I'll just pop it from my stack, right? Now if the stack still has some elements, I'll check my candidate answer. So the top of the stack will be my candidate answer, and I will directly update my inter of I with my candidate answer. And after it, I just push the current element into the stack, right? So this is what I've done. After all this is done, after the processing from the left side is done, I remove all the elements from the stack and I start processing from the right side. So I'm starting from n-1, right? Again the same thing. While there are some elements in the stack and the top of the stack is greater than or equal to the current value, I just pop it from the stack. Now again, if there are some elements remaining in the stack, only then I'll process this particular part. So you see, this particular part is all the checking I have done just to check whether my new value is better than the previous value. So here I get the candidate answer, which might be a candidate for the answer. So this is the new value that I'm getting from stack.top. Now I just check whether the current element is -1 or -1 in the intermediate answer. So if it is -1 comma -1, that means I have not got an answer for this particular index till now. In that particular case, I can directly update my answer, right? Otherwise, it means I already have an answer for that particular index. Now I compare x and y. So x is the distance of the initial tower that I have taken from the left, and y is the distance of the tower from the right. I've also created a boolean variable called change. So this will denote whether I have to update my answer or not. So if the new distance is less than x, then I can directly mark change as 1, right? Otherwise, if both of the distances are equal, I'll compare whether the height of the first tower or the new tower. So candidate is the new tower, right? So I have to check whether the height of the new tower is less than the old tower or not. If it is less than the old tower, I'll mark my change variable as 1. Again, if it is false, I'll just check whether the height of both towers are same. In case they are same, I have to check whether the index of the new tower that I have got is less than the index of the old tower. In this case, I'll mark my change variable as 1, right? And if the change variable is true, that means I have to update my value. I have set my enter of I as candidate, right? After all this is done, I just push my current element into the stack. Now I create my answer vector. In the answer vector, what I do is I just traverse through the whole array and mark the answer of I as enter of I dot second. So this will be updating my value. And because the second index has the indexes, so that is why I'm showing it in my answer vector. And after all this is done, I'll just return my answer. So this would be the whole solution, and let me just also submit it for you. So the next time any such thing happens, you know that this code was passing all the test cases when I solved this problem, right? So you can see like all the test cases passed and this has been solved successfully. So that is it for today's video, and that was the solution for today's problem of the day, nearest smallest tower. I hope that you guys were able to understand the solution. If you guys did, then do consider dropping a like on this video and subscribe to this channel. It's always free of cost, and you can always unsubscribe if you don't find the videos interesting later. I see that a lot of people who watch these videos have not subscribed yet. So if you are one of them, then please do consider subscribing and share the channel with your friends. Till the next video drops, keep coding, stay safe, bye bye.